Okay, so let's have a look then at magnitudes. Okay, or the magnitude scale as it's sometimes called. A good way to get your head around this is to think about the brightest star in the sky. What's the brightest star in the sky? So the brightest star in the sky is the sun. And can you imagine just the faintest star that we can see from Earth? So we're talking Hubble Space Telescope on its bestest setting, a star that just manages to record 1 pixel or something. Can you imagine that? So literally the faintest thing you can possibly imagine. So down here would be very faint things, and up here would be very bright things, okay? Now, can you see a bit of a problem, or the problem that astronomy faces, is just the range of brightnesses. If I call the faintest star that we can possibly see with the most powerful telescopes in orbit around the Earth 1, what number would I have to have for the sun? And just feel your head just going, it's just going to be bonkers, isn't it? It's not going to be a million, it's not going to be a million million, it's not going to be a million 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 million, it's just going to be a colossal number, isn't it? All right? So the problem in astronomy is our scale of brightness, okay? It has just a ridiculous range to cope with, okay? Most temperatures, we were talking about temperature earlier on, air temperature on the Earth, 100 degrees would cover it, wouldn't it? Easy, yeah? Minus 40 in somewhere cold to 40 somewhere else. 100 degrees, no problem at all, okay? But the range of brightnesses in astronomy is just bonkers. You're going from things on the limit of our technology to just resolve as a single dot to this thing which is turning the sky, it actually is today, actually turning the sky completely blue because there's so much brightness, it blots out everything else, even Sirius, okay? So that's the problem we have in astronomy, is how do we deal with that enormous great scale, okay? I think you can see an ordinary number system is not going to work, all right? Starting off with 1 for this, well, a star twice as bright as that would be 2. By the time you get to the sun, you're just going to be in a ridiculous state, okay? These types of scales are quite common in nature, but actually, in most of the science you do at school, the people who organise that sort of thing seem to work very hard to make sure you never study them, all right? The other very famous one is sound level. If you went from the quietest whisper you can just about hear to having a jet aircraft take off over your bedroom. Again, if that was 1, this is 1, how loud is that? It's just enormous, isn't it? Human hearing is pretty incredible stuff, and you can actually cope with enormous range of sound level. The way we get round that, if you want to look into it, is the decibel scale. You might have heard about that. The decibel scale is quite unusual. It works in a different way to something like temperature that just goes 0, 10, 20, 30, 40, 50, up to 100, okay? A scale like temperature that you're very familiar with, okay? Where the 0 is up to you, but basically it just goes up in a range of ordinary numbers. The decibel scale works in a different sort of way, okay? And in astronomy we have a scale of brightness which works in quite a different way, okay? So the key thing is to understand the problem. We've got to get a range of numbers without getting 38 noughts on the end or something bonkers like that. We've got to get a range of brightnesses into a sensible scale of numbers. Most things that you study in science, temperature, mass, volume, area, there's no real problem with them. Numbers just sort of fit quite nicely. But in astronomy, we need to solve this problem. We solve it using what's called the magnitude scale, or the scale of magnitudes. Okay? And it works a bit differently to most scales of numbers that you've probably come across before. Okay? Now, there's a number of things that are quite strange about it. For example, the number in the middle is 0. All right? So, in what ways is the magnitude scale a bit unusual? Well, let's start the list. The first one is it is 0 in the middle. Okay? The second thing is it's minus for bright things and plus for faint things. So it's upside down. All right? And obviously you can see the potential for getting this wrong. So you need to keep your wits about you with the magnitude scale, because it's got a number of strange features, okay? It's not 0 at the bottom like temperature was supposed to be, although we keep finding colder and colder things. It's 0 in the middle, roughly, and it's upside down. So the smaller the number, the brighter. The bigger the number, the dimmer. Okay, and in fact, very, very, very bright things have negative numbers. The sun's magnitude, for example, at the moment is negative. Okay, Sirius, we mentioned earlier, again has a negative magnitude. Okay, now what we need to do is get around this big range of brightnesses, and of course we can't do that just by doing that. We've got to do something a bit special. Okay, and what brightness is going to be here? It's going to be -1, okay. Next brightest magnitude will be -2, do you see? All right. Slightly fainter than 0 is +1. Slightly fainter than +1 is +2, and so on, okay. Now, as I said, this on its own isn't going to solve any problems, particularly where you put your 0, which are around your scale. That doesn't solve the problem of the enormous brightness difference. What we do there is something a bit unusual, which is as you go each step. So imagine you went one step on the magnitude scale, and the question is, how much extra brightness is that? Well, if you compare it with, I don't know, something like mass, let's go 1 kilogram, 2 kilograms, 3 kilograms, 4 kilograms, okay? How much mass do you add by going up one step on this scale? You obviously add 1 kilogram. If I went from 4 kilograms to 5 kilograms, how much extra mass is that? It's 1 kilogram, isn't it? If I went from 1,000,000 kilograms to 1,000,001, it's still 1 kilogram, isn't it? This is where the magnitude scale is a bit different, okay? You don't add any particular amount of brightness. What you do is you multiply by 2.5, okay? Which seems a bit strange and is actually very unusual, all right? The science that you do in schools these days, you tend to avoid scales like this, I don't quite know why. But what it does is, as you go one step on the magnitude scale, you don't add a certain amount of brightness. What you do is you multiply all the previous brightness by 2.5, okay? If you then went up another scale, another step, again, you're going to multiply by 2.5, okay? If you went from 0 to 2, so -2, beg your pardon, how many times brighter is -2 than 0? Because you're all thinking 5, aren't you? Because naturally, you'd add up, wouldn't you? If this was like kilograms, if I go from 1 to 3, that's obviously 2 kilograms, because each step is an extra kilogram. Now, this scale doesn't work in that way, all right? You don't add a particular amount, you multiply. So the sum you need to do to go 2 steps in brightness is 2.5 times 2.5, which is about 6.25, all right? So -2, how much brighter is it than 0? It's 6.5 times brighter, okay? It's not that you obviously do add some brightness with every step up the scale, but it's not what we might call an additive kind of scale. It multiplies at each step, okay? And these types of scales are surprisingly common in nature, and as I said, surprisingly rare in school science for some reason, okay? And this is why this takes a bit of getting used to, because it's different to pretty much any scale of anything. It's different to pretty much any scale of anything that you've probably come across before, okay? So let's make perhaps a little chart here. If you went up on the magnitude scale, the question is, what would you do to your brightness? If you go one step on the magnitude scale, you'd multiply your brightness by 2.5 times. So think of it like money. If you had £100 and you went up a magnitude, you'd have 250. Okay? If you went up 2 steps, you wouldn't have £500, you'd have 625. All right? It's a bit like interest, I guess. If you had £100 in the bank, you put £100 in the bank, you got 10% interest. How much money would you have at the end of the first year? You invest £100 at 10% interest. How much money would you get at the end of the year? You'd have 110, wouldn't you? How much would you have at the end of the second year? It's 121, isn't it? Because in the second year, you'd earn 10% of 110, which is £11. Do you see? It's what's called compound interest. And that's why, if you leave money in the bank for long, long periods of time, even quite a small rate of interest, Well, 10% is quite a big rate of interest. But if you work out in your calculator, do 1.1 times 1.1, you get 1.1, 1.21. Do you follow? And it's not 110, 120, 130. It quickly gets much bigger than that, doesn't it? Okay? So it's a bit like, if you want to think of it in terms of money, which is a good way to get the right answer, it's a bit like compound interest, all right? At the end of the first year, you're earning interest on what you started with and the stuff that you've earned as interest, okay? 3 years, sorry, 3 years, now. 3 magnitudes. The sum you need to do is not 2.5 times 2 plus 2.5 plus 2.5. It's 2.5 times 2.5 times 2.5, okay? Which is approximately 16, not exactly 16, it's about 16, okay? So 3 magnitudes is 16 times brighter. Not an extra 16 chunks of brightness, 16 times what you had before, okay? You don't need to know them all the way up, but it's useful to know the first 5. You'll see why in a minute, okay? What sum do I need to do in my head to work out 4? What short sum can I do?
16 times 2.
It's 16, it's the previous one times 2.5, which is easy, isn't it? Because it's 2.5 16s, it's 40. And that gives us a very nice number for 5, which is 100. Okay? Generally, if you know the first 5, although they're not the first 5, because you can apply them anywhere. If you went from minus 17 to minus 22, it would be 100 times brighter. Okay? 6 is easy to work out. Be 250, won't it? Because it's 100 times 2.5, not 102.5. Do you follow? It's not adding a certain amount each time, which is what most things in science do. This one, you times everything that you had before. Okay? Does that sort of make sense? Yeah? To see why you'd end up with such a big range, I'm always reminded of, we don't need to draw this, it's just a bit of silliness. There's a story, one of the great Greek philosophers, Archimedes or Aristotle or somebody, apparently the legend goes, they were did some great service for the king or something, and he said, well, what can I pay you in? And they offered him various bits and bobs, and he said, no, all I want is a chessboard, and on the first square, can you put 1 gold coin? On the second square, can you put twice as much as the one before? Are you with me? Now, there probably isn't that much money in the world. Can you imagine? You try and calculate 2 times 2 times 2 times 2 times 2, 64 times. It's obviously 2 to the power 64, which is a very, very big number indeed. It's the same principle. Are you adding a certain amount of gold each time? Is the amount of gold you're adding each time the same? Well, how much gold would you have to add on the second square? And then on the third one? Be 2, wouldn't it? So it's not like this. Do you see? You're not adding a certain amount with each step, are you? What you're doing is you're timesing. So this has to have twice of that. So that's 1, 2, 4, 8, 16, 32, 64, 128, 5, 12. And pretty quickly, by the end of the first row, you're up to massive amounts, aren't you? Okay? So the point about this scale is this is a good way of thinking about the magnitude scale. Why does it build up so quickly? Is because what you're doing, a bit like compound interest, is timesing the one before. But it's a bit like a 250% interest rate. Very quickly, after 1, 2, 3, 4, 5 years, you're quickly up to 100 times what you had before. Okay? And that's how, I think you can see, we take this enormous range of brightness from the sun to the faintest thing possible. And I can never remember the exact numbers, but minus 20 something, 24, 25 is the sun, and at minus 25, plus 25, would be around about here, okay? I don't know exactly how faint the Hubble Space Telescope can see, but if you go this range of about 40, 50 numbers, if you go from minus 25 to plus 25 on this scale, you cover an incredible range of brightness. Think of the gold coin thing. It's almost about the same, isn't it, 50 squares? And quickly you've covered the most enormous range from a single gold coin to more money than there is in the world, probably. Okay? So using this multiplying on each step, not adding, that's the key phrase to remember from this. By multiplying at each stage instead of just adding, like we do with kilograms or pounds of potatoes or something, by multiplying on each step the total amount that you had before, okay, And you can try this sort of thing at home, try it with grains of sand or something, quickly, it just gets ridiculous, okay? You quickly develop this enormous scale, and the brightness of the sun can be on this scale about around minus 20 something, and the faintest things we can possibly see are, although this probably changes every minute, around about the plus 25s there, you've got an enormous range of brightness, okay? Is everybody happy with that? Okay. Now, unsurprisingly, the human eye is sort of centered around the zero. Where do we fix the zero? Round about the bright stars of the night sky. All right. So if you look up famously bright stars like Sirius, you have in here. You have the planets, obviously, because they're brighter than the stars, aren't they? After that, you have the moon, and so forth. Okay. They all fit in here with minus numbers, as you can imagine. Okay. The bright stars are minus numbers. Sirius being a good example. A lot of stars are plus 1, plus 2. The human eye, we reckon, can see down to round about, it varies a lot, it's often quoted as plus 6. Okay? Now, you need to work pretty hard to see a plus 6 star. You need to go somewhere very, very, very dark, with absolutely no light pollution, absolutely no moon, completely black sky in the middle, looking south at midnight, etc., etc. In theory, the human eye can get down to around about plus 6. But if you look up a constellation you can see from your back garden and look up the faintest star you can see, it won't be anywhere near plus 6. Okay? But in theory, that's the sort of theoretical limit for where we can see. Okay? So there's an awful lot of stuff way below that. 20 magnitudes. And 20 magnitudes is a lot of brightness. Can you imagine that? 2.5 times 2.5 times 2.5, 20 times. Okay? In fact, we can work it out from here, can't we? 20 magnitudes is not 400. So it's 100 million, isn't it? Yeah? Things from there to there is about 100 million levels of brightness, isn't it? Okay? So that's roughly how the system works, with the human eye round about 0 but going down to about plus 6. Obviously you can see things brighter than that. Okay? With telescopes and things like that, what we're obviously doing is improving. I was going to say reducing, but that's not, it's odd, isn't it? You're looking at something fainter, but the actual magnitude would be a bigger number, all right? So say fainter or dimmer, sorry, say fainter or brighter. Don't say a bigger magnitude, because that can be very confusing. Do you mean a bigger number, which is actually a fainter star, isn't it? All right? So we can, with telescopes and binoculars, we can gradually push this limit, we can push this limit to fainter and fainter stars. And as we say, the most powerful telescopes on Earth, or around the Earth, can now see well down into the plus 20s, okay, which are hundreds of millions of times fainter than what you can see with the naked eye. Okay? So, it's got naught in the middle, it's upside down, and it has this very strange multiplying on each step. Okay? But if you think of the chessboard problem, you can see why, because by doing that, you allow a sort of a 50-point scale to cover this incredible, literally astronomically large range of brightnesses. Okay? Now, this scale of magnitude we just talked about is called apparent magnitude. What do we mean by apparent magnitude? We mean being on planet Earth, where most of us live, and looking out at the night sky. If you go out in the night sky, and people did this thousands of years ago, and they said, look at those stars, aren't they lovely and bright? Let's make a league table. Let's make a table of brightest stars, next brightest, like first division, second division. Do you get the idea? That's why I sometimes remember it. The first division stars, the second division stars. Why is that a good way to remember? Because, of course, as the number of the division gets bigger, the brightness of the star gets lower. Do you see? So think of football leagues, although they've got clever names, haven't they? But think of it like first division, second division. That's a good way to think about it. First division stars are much brighter than second division stars. All right? And literally, this is what people did in ancient times, and they came up with this scale of brightness. It's really interesting to go back and look at them, because, of course, some of them have changed. We know that some stars are variable, because if you go back to the very first magnitude scale records, where people put all the famous stars like Sirius and all the ones in the Plough, etc., they put them into this system, and you compare them with how they look nowadays. What you often find is there's some changes, because some stars over thousands of years have actually changed their brightness. Some stars we know to be variable because ancient records put them in a different division. They put them at a different point in their division compared to where we have them now. Okay? The key thing you need to know is that if you look with your eyes from the Earth, that's called apparent magnitude. What number does the star have on this scale is called apparent magnitude. Okay? Now, there's a big problem with apparent magnitude, which is why there's another kind of magnitude. As top scientists, can you see the problem with apparent magnitude? Yeah. According to apparent magnitude, what's the most powerful star in the universe? Well, no, you're right. First answer, the sun, isn't it? Yeah. According to this system, this tiny dot that you can just about see with the Hubble Space Telescope might be some massive supergiant star, millions of times more powerful than the sun. And according to this system, the sun is millions of times more powerful than anything in the universe. Now, that's a load of old rubbish. Why has the sun got such a high apparent magnitude? Yeah, because it's really close, isn't it? Nearest star, 4.5 light years. The sun, we're practically on top of the sun, aren't we? Yeah? So there's a big problem with apparent magnitude in that, in scientist terms, it's not a fair test because it depends on the power of the star. It also depends on the distance. And as you know, in science, we don't like to have things which are kind of affected by two variables. It's like not a fair test, we say. Okay? So if you line stars up, and this is kind of what I've done roughly, I think in the handout there's a better one, isn't there? It's in the previous one, isn't it, about stellar evolution? Remember the one about stellar evolution, the handout? Yeah, I think in there there's a better drawn out scale of this. Okay? But if you arrange the stars and all the things in the sky in terms of their apparent magnitude, what does that tell you about the objects? It tells you nothing. Because a star's position on the apparent magnitude scale depends on two things. It depends on the power of the star, which is quite interesting, and it depends on the distance of the star. So you look out and you say, the sun, is it the most powerful star? Well, no, it's not the most powerful star in the universe. It's the distance that's giving it a massive advantage. If you look at Rigel in the constellation of Orion, the blue star in Orion, it doesn't look particularly bright. It's quite bright, but it's not massively bright. Why is that? Well, it's because it's an enormous distance away. And it's actually many, many times more powerful than the sun. But it doesn't look it. It doesn't compare on the apparent magnitude scale very well because it's got a huge disadvantage. It's an enormous distance from the Earth compared to the sun, and that's why it looks like a tiny speck, whereas the sun, which is an extremely average star, completely covers our whole sky. Okay? So basically what we need to do is to make a more useful one. Okay? We need a more useful magnitude scale. The magnitude scale is fine, the numbering thing, the 2.5, the 0, the minuses, that's all fine. But the problem is, if you go outside in the night sky and do it with your eyes from Earth, you end up with something which is quite interesting, but not very useful. All right? What we need to do is to factor out the distance. Okay? We need to invent another way of lining up the stars on the magnitude scale, which doesn't involve distance. Now, this you kind of have to do in your mind because we can't do this in practice. But let's imagine on the Earth here, let's suppose we got all the stars that there are, and we said to them, right, what we want you to do is to fix yourselves at a certain distance. So we said to the sun, well, you've got a huge advantage, you're way too close. Can you imagine like lining runners up at the beginning of a race? You with me? Like you've got loads of people running up for a race, and they're all staying at different distances from the finish line. You say, well, that's not fair, you're too far back, you come forward, you go back a bit because you're too close. You'd want them, you ever seen the beginning of a race? Basic rule of racing is you all cover the same distance, don't you? So you line people up at the same distance. So think of it like that, trying to get people organised for the start of a race. You say to them, I want this to be a fair test. That's the proper sort of scientific way of thinking about it. We want it to be a fair test. And so what we have to do is get rid of this distance disadvantage or advantage which stars have. Most of them, of course, have a disadvantage. And what we do is we fix a standard distance, and that standard distance is a distance of 10 parsecs, which they use in Star Trek a lot. The parsec we'll come back to later, you just need to know it's 3.26 light years. Okay? It doesn't matter what the distance is, it could be 20 parsecs, it could be a million, it could be 6 3/4, it doesn't make a difference. The point is, on this second system, what you do is you line the stars all up at the same distance. Now, this obviously has to be calculated. You can't actually do this. But if you were to imagine doing this, then you would have measured something called absolute magnitude. Okay? Now you mustn't muddle these up because they are fundamentally very, very different. Okay? Apparent magnitude does what it says on the tin. You look out at the night sky or the daytime sky and you see how things appear from the Earth. Okay? It's what you see. The problem is, in terms of studying the stars and understanding what they're doing and comparing stars, it's not really very useful because a star having a high apparent magnitude, it's useful if you want to find it. If I say to you, there's a really interesting star outside tonight, let's go and have a look at it. It's got a magnitude of +8. What would you say immediately? You're able to see it. Not unless you've got a telescope or a pair of binoculars, +8, you're able to see it. So apparent magnitude, somebody once said to me, apparent magnitude is useful for astronomy, whereas absolute magnitude is useful for astrophysics. All right, it's a bit of a naff way of thinking about it. But in principle, if you want to find things in the sky from Earth with a telescope, with your eyes, with binoculars, apparent magnitude is what you need to know. Okay? Absolute magnitude, though, is more useful to scientists. That's not a very good way of explaining it, but it's kind of right because absolute magnitude tells you about what the star's actually like. Do you see? Absolute magnitude links only to the power of the star. All right? Think of it like a sort of an astronomy fair test because apparent magnitude really isn't. Because when you look out at the night sky, you're seeing powerful stars, weak stars, nearby stars, distant stars, and because of those two variables, you never really quite know what you're looking at. Okay? Absolute magnitude depends on only one thing. I've discovered a star, it's got an absolute magnitude of -15. Tell me about that star. It's got an absolute magnitude of -15. What sort of star might it be like if we went to visit it? What would it be like? -15. Be a really powerful star, wouldn't it? Be very powerful indeed. An absolute magnitude of -15. If you're high up on the absolute magnitude scale, what does that mean? It means only one thing. You're a very powerful star. All right? You're chucking out an awful lot of light. Okay? -15 on the apparent magnitude scale. Could mean you're very powerful, it could just mean you're very close by. You don't know. All right? So it's horses for courses. This is useful for looking at the sky, but it really tells you nothing. All right? I can see a really great star. It's got an apparent magnitude of -2. Tell me about the star. Apparent magnitude -2. What can you tell me about the star? But what can you tell me about the star itself? Nothing. You don't know, do you? It is very bright from the Earth, but is that because it's close? Or is it because it's very powerful and far? You don't know. It's like the eternal triangle of astronomy. Something looks bright in the sky, you just don't know. It could be because it's really close and not actually very powerful, or it could be a really long way away and really, really powerful. You don't know. Okay? Absolute magnitude kind of solves this problem. All right? Standard distance, 10 parsecs, 32.6 light years. You'll need to remember in a minute. And absolute magnitude is really important in astrophysics because it tells you about the star. If you know the star's absolute magnitude, you might think, well, how on earth do you ever know that? We'll come to that in a minute. But if you know the star's absolute magnitude, you know something about the star itself. Yeah? Absolute magnitude -15, that is a seriously powerful star. It is chucking out millions of times more energy than the sun. It is a really powerful star. Okay? If you look back in the previous handout, the previous PDF, not the one about the celestial sphere, the one about evolution of stars, I think what it does, it lines up a load of stars in terms of apparent magnitude and then reorganises them in terms of absolute magnitude. Okay? A good example would be the sun at about -26. On the apparent magnitude, I think I'm right in saying it comes in at about +4.5 on the absolute magnitude scale. Tell me what the sun's really like then. It's not really a very powerful star, is it? It looks very bright in our sky, apparent magnitude, but when it's got an absolute magnitude of +4.5, you know it really isn't a particularly powerful star. Okay? Something like Rigel, down here, I can never remember that, -1 or something, on the absolute magnitude scale is minus whatever. It's really powerful. There's an example of a star a long way away. It looks quite bright from the Earth, but in reality is a tremendously powerful star. How can that happen? You have to put the star a long way away. How can you get a really, really powerful star to just look quite, small in the night sky? You obviously have to put it a long way off. Okay? Right, final thing we need to do then is to link up these two things. Just lose that bit off there. Okay? So the three things we're doing today, we've done apparent magnitude, which is little m, and we've done absolute magnitude. If you say them quickly, they don't sound very different. That's not very good. Okay. When you're writing these with your pens, it's important to make them different. All right, so it's really clear. Are you writing a little m for apparent magnitude or a big M? I tend to put little feet on, little serifs on the bottom. Like the Times headline, Times New Roman. Just put little feet on your M so it's really clear that's a capital one, because in some calculations it's going to be important that people can tell what you're doing. Okay. Now, pretty obviously, there is a link between the distance of a star, its absolute magnitude, and its apparent magnitude as it appears on Earth. Those three things are obviously linked together. Okay? The apparent, the absolute, and the distance. Okay? If I change any two of them, I'll obviously affect the other one. Okay? And you could be asked to convert between the two. Now, there's various ways of doing this, and the one I like is this one. Okay. There's various ways of converting between absolute and apparent magnitude. To do that, you would obviously need to know the star's distance, and this is the formula, which is the easiest way of writing this. I think if you look in your specification, they write it in a slightly different way. Okay, but it works exactly the same. This I find the neatest way of writing it. I think in the specification there's a slightly different version, but it does the same job. Okay, so let's have a go at using this then. Let's take an example. Let's suppose here we are on Earth and we look at a star in the night sky and it appears to have an apparent magnitude of -4. So how does it look? Pretty bright. Yeah, it's up there with the planets, I would think. I can never remember what Sirius is, but it's not as bright as that. So it's a very bright looking star. Okay. And we happen to know, by magic, that it is 1,000 parsecs away. Okay. And the question then is, if we've got all that information, can we calculate its absolute magnitude? Okay. Let's have a go. Let's walk through this one together. First thing is we need the formula. Big M equals little m minus 5 times the log of d over d. Okay. Little d is obviously the distance. Okay, so little d is the distance of the star. Big D is your standard distance. Do you remember we said absolute magnitude is like a fair test for stars? We line all the stars up at the same distance from the Earth. Well, the distance we happen to have chosen in astronomy is 10 parsecs. All right? So capital D here is 10 parsecs. All right? So all you have to do is put your numbers in. Little m, be careful with your pluses and your minuses. If you hate that thing in math where they make you take away a negative number, this is going to happen sometimes. All right? So you need to be careful with this. Little m is -4, because little m is the apparent magnitude. Okay? And then it's -5 times the log. And it's best to do this bit in brackets first. Remember Bod Mass? Do you do Bod Mass? Bid Mass? Yeah. So do your bracket first. Little d is 1,000 parsecs. And big D, you never even have to look it up. It's always 10 parsecs. Okay? So let's just write it out to keep it clear. -4 minus 5 times the log of, well, 1,000 over 10 is 100. Can you see? 1,000 parsecs over 10 parsecs is going to be 100. I'm run out of board now. Let's make some space. So let's go up here. So I'm going to have big M equals, I'm doing it in tiny steps so we get it right. Right, this bit here, log of 100, Once you've done these for a while, you can get to know these in your head. But if you've got a calculator, log of 100. Either using your brain, after a while you get to know these, but you need a calculator. So for the exam, you'll need a calculator that can do logs, because sometimes it might be a number you can't do in your head. All right, but yeah, log of 100 is 2. All right, so if you put 100 into your calculator and press log, all right, if you never use that button on your calculator very much, you need to get to know where it is. If you've got a calculator that hasn't got a log button, you need to get one for the exam. All right, and your scientific calculator. All right, some calculators you put 100 in and press log. Other calculators you press log and some brackets come up and you type in 100 and press execute. I don't care. You need to sort it out for your calculator. Okay, is everybody happy? Log of 100 is 2. It is equal to number of noughts, but sometimes they're numbers that have just noughts on the end. Okay, so we're left with minus 5. 5 2s are 10. Minus 4 minus 10 is minus 14. Tell me about the star. It's a yes. It's a very powerful star. Is it? Even the word brightness, you've got to be careful with, haven't you? Do you mean brightness? It looks from the Earth. Do you mean? So the word powerful is better, isn't it? It is quite bright from the Earth, isn't it? Minus 4. It's a very bright star. But actually, it's doing minus 4. It's doing minus 4 while it's still 1,000 parsecs away. All right? It's 1,000 parsecs away and still looks minus 4. The only way that can happen, it's quite a long way off, and it still looks really powerful. The only way you can do that is to get a big number there. Okay? The thing's kind of self-checking. Let's suppose you did minus 4 plus 10, which is the most obvious mistake, isn't it? That would give you plus 6. Now, this is kind of self-checking. This does seem like a bit of a mystery thing. You shove numbers in, you press these log buttons, and this number pops out. But at the end of it, you can still check. You can still check that it makes sense. It is easy to make a mistake here. And let's suppose we've made the most obvious one, and we've wound up with the answer plus 6. Okay? Hopefully in the exam, you would look at that and think, no. Because, yeah, but it's more than 10 parsecs away, isn't it? At 10 parsecs, it would appear to be minus 4, wouldn't it? This thing is 1,000 parsecs away, and yet it appears minus 4 from the Earth. It needs to be a really powerful star. Plus 6, remember the scale? Plus 6 is quite a low number, isn't it? It's got to be at least bigger than minus 4, isn't it? If we put this star at 10 parsecs, it would appear to be minus 4. Yeah? And yet it's actually further away than that. And yet it appears to be minus 4. So it must have a magnitude better than minus 4 to start with. And so minus 14 looks right, doesn't it? All right? So although it's a complicated thing, a funny formula with logs and stuff that you never use, at the end of it, just stop for a minute, because this will be quite a lot of marks in the exam doing this. If you get it wrong, you're going to lose a lot of marks. Please make sure you check your answer. I know it's difficult because it's upside down, it's plus and it's minus and stuff. But you can use common sense. Minus 4 at 1,000 parsecs. As soon as you start the question, you want a number like minus 10 or something, don't you? And minus 14 obviously fits the bill. If you just lose your minus sign and get plus 6, hopefully in the exam you would spot that and think, hang on, I've done something wrong here. I need to go back and check it because plus 6 can't be right. A star of plus 6, 1,000 parsecs, you'd never see it, would you? Plus 6 means that from the Earth at 10 parsecs you could just see it. But where is it in this question? 1,000 parsecs, you'd never see it. There's no way a star at plus 6 at 1,000 parsecs could be minus 4. All right? This equation has a brand name. It's called the distance modulus equation or formula. Okay. I think in your spec they give it a slightly different format, but it doesn't really matter. You just shove the numbers in and out comes the answer basically. But do be ready to check it. Okay. Right, let me set you one and see if you can do this one. Let's turn it the other way around. Okay. So here's egg 2. I'll leave egg 1 on the board so you can have a look at it. Here's egg 2. Here's the Earth. Okay. We've discovered a star which is minus 20. It has an absolute magnitude of minus 20. But the problem is, it's at a distance of 1,000,000 parsecs. Can you tell me how bright will it appear on the Earth? In other words, what's its apparent magnitude? And be careful, because I've muddled you around there. Okay, so example 2, here we are. Minus 20 is its absolute magnitude. It's capital M, is minus 20. It's a distance of 1 million parsecs, and the question is, can you calculate little m? Formula big M equals little m minus 5 log d over d. But I'm asking you the m's the other way round, so you have to be a bit cunning. The easiest way is put numbers in and swap it around afterwards. You can swap the equation around first and then put numbers in, it's up to you. I don't mind how you do it. Everybody get 5? Okay, so if we run through it, just put numbers in. Big M is minus 20, because I've told you the absolute magnitude this time. Little m you don't know. If you want to rearrange the equation first for little m and then put numbers in, it's up to you. I prefer to put numbers in and then work out afterwards. Minus 5 times the log of the distance is 1 million parsecs. Over the big D is the standard 10 parsecs. So you're left with 1 million over 10, which is 100,000. Log of 100,000 is 5 on your calculator. So log of 100,000 is 5. 5 5s are 25. You're left with minus 20 is little m minus 25. So I'm thinking of a number. If I take off 25, I get minus 20. If you don't like this sort of thing in math, the easy way, I think of it like a number problem. Little m is the magic number I'm thinking of. If I take off 25, I get minus 20. If it was your bank account, you'd work it out fast enough, wouldn't you? I'm thinking my bank account, if you take £25 out of my bank account, I've got £20 in debt. It's pretty obviously I've got £5, haven't I? Yeah, not minus 45. Little m is 5. Okay? There's various math ways of doing this sort of thing, but that's what you need to be able to do. Anyone not happy with 5? How would it look from the Earth? Quite dim. Would you be able to see it with naked eye?
Yeah, you just about.
Just about. Alright. Plus 5, you would just about be able to see with naked eye, I think. It's on the limit of what you can see. But that makes sense, doesn't it? Because it's a powerful old star, minus 20, but look how far away it is. It's 1 million parsecs away. So this 10 parsec standard distance is just a huge distance away. And as you can see, distance is a bit of a killer for brightness. You end up with an apparent magnitude of just plus 5. Okay. And this is some of the night sky stars. Some of the really faint ones you're going to just see actually are tremendously powerful stars, but they are an enormous distance away. With apparent magnitude, you just don't know. With absolute magnitude, you can start to separate the distance from the absolute magnitude. Okay?